Power doesn't just multiply on its own, and yet, that's exactly what some devices claim to do. At first glance, the idea sounds almost irresistible. A small system that takes in a bit of energy and somehow produces more than it consumes. For anyone dealing with rising electricity costs, unreliable grids, or a desire for independence, that promise hits something deeper than curiosity. It feels like a potential way out. So people start looking closer. They watch demonstrations. They see diagrams. They hear explanations about efficiency, optimization, and hidden losses in traditional systems. And for a moment, it all seems plausible. After all, we know that most energy systems waste something: heat, friction, resistance. So what if someone finally figured out how to reduce those losses enough to make a meaningful difference? That's usually where the journey begins. Then comes the experimentation phase. People try to understand how these devices work. They compare them to solar panels, batteries, generators. They look at input versus output. They try to reconcile what they're seeing with what they already know. And that's where things start to feel off. Because even after accounting for efficiency gains, the numbers don't quite line up. The output seems higher than expected, not just slightly improved, but disproportionately larger. And that raises a quiet but important question: where is the extra energy coming from? At this point, most explanations start circling around similar ideas. Concepts like resonance, frequency alignment, magnetic interaction, or energy recovery loops. These terms sound technical, and in some cases, they are rooted in real physics. But the way they're combined often creates an illusion of something more than what's actually happening. The frustration builds here. Because on one hand, there's a desire to believe there's something new, some overlooked mechanism that changes the game. On the other, there's a growing sense that the explanation isn't fully grounded. That maybe the system isn't creating energy, but simply redistributing or temporarily storing it in a way that looks like multiplication. And that distinction matters more than it seems. Most people approach this from a surface level, input versus output. If the output appears higher, the assumption is that something extraordinary is happening. But what's often missing is a deeper look at the structure behind the measurement. Energy systems are rarely as simple as a single input and a single output. There are delays, accumulations, hidden sources, and measurement gaps. A battery can discharge faster than it charges for short periods. A capacitor can release stored energy quickly, creating spikes that look like amplification. Mechanical systems can store kinetic energy and release it in bursts. So what appears to be multiplication can sometimes be timing, or perspective, or incomplete measurement. And this is where the conversation usually shifts. Because the real issue isn't whether a device can improve efficiency. That's already well understood, many systems do. The real issue isn't even whether new configurations can produce better performance. They often can. The real issue isn't energy multiplication. It's misunderstanding how energy flows through a system. Once you start looking at it that way, things begin to change. Instead of asking, is this producing more energy, the question becomes, what is this system actually doing differently? Is it reducing losses? Is it storing energy temporarily? Is it changing the rate at which energy is released? Is it using an external source that isn't immediately obvious? These questions don't make the idea less interesting, they make it more precise. And that precision is what most people are actually looking for, even if they don't realize it at first. Because underneath the curiosity, there's a practical goal. People aren't just interested in theoretical breakthroughs. They want something that works, something reliable, something that can be understood and, ideally, replicated. That's where clarity becomes more valuable than excitement. When you step back and look at these systems through a structural lens, a pattern starts to emerge. The most convincing setups are often the ones that simplify the explanation. Not the ones that stack multiple complex ideas together, but the ones that clearly show where energy enters, how it moves, and where it leaves. That doesn't mean every claim is false. It means that every claim needs to be grounded in a complete picture. And that's the part that often gets overlooked. Because it's easier to focus on the result than the process. Easier to look at output numbers than to trace the full path of energy through the system. But without that full path, it's almost impossible to know what's really happening. So instead of thinking in terms of more energy, it becomes more useful to think in terms of better understanding. Understanding where inefficiencies exist. Understanding how energy is stored and released. Understanding how measurement can distort perception. That shift doesn't just apply to these devices, it applies to any system that claims to outperform expectations. And once that perspective is in place, something interesting happens. The confusion starts to fade. Not because every question is answered, but because the right questions are finally being asked. And those questions lead to something far more useful than a quick conclusion. They lead to a clearer framework for evaluating any energy system, no matter how convincing it might seem at first glance. If you want to explore that framework in more detail, there's a structured breakdown in the description that walks through how to analyze systems like this step by step. And if you're interested in understanding these kinds of mechanisms more deeply, you can subscribe for more grounded, technical explorations like this.